Just a second. Fine. Share the screen then. Is the screen visible? Okay. Okay. Uh, so in the last session was joined live by two students, and they requested that we divide this session into two parts. In the first part, we should revise the contents of the first 4 weeks of this course, and then in the later part of this session, we can discuss things related to the week 11th session, which the lectures which I am assuming you would have already gone through. So, should we first start with the revision part? Is everybody fine with that? Okay. So this was the week 1 part. So what I'm doing is I'll go through the problems, okay, one by one, and ask you if you have doubts related to the concepts that were taught in that session, and uh, and we'll see how this session would go accordingly. Okay. And this would be also beneficial for you since, I mean, this is, I guess, second last session, I guess. Second last live session before your exams, right? So that's why this might be useful. So let's start with the first problem. Please try to be as interactive as possible, okay? Because uh, I need to understand your doubts because these problems I've already discussed, right? Now, if because some of the students did join this course late, so it might as well occur that you might not have joined this particular live session at that point of time. So if you have any doubt, you can ask it right now. Okay. So the first question stated that which band would result in heavier electron mass. Okay. So we were given two EK curves. The curve A, which is denoted by the solid line, and there is this curve B, which is denoted by the dashed line. Okay, so as you can see, the difference between the two curves is that both of them have different curvature, right? Just a second, I should switch on my camera, right? Uh, is my video visible? Yes, I guess, right? So, so how did we proceed on this one? We use this formula, right? That your effective mass is inversely proportional to the curvature and is given by this particular formula. Your h bar square by dou 2e by dou k square. This is curvature, okay? The derivative of dou e by dou k is called curvature of Vk plot. Okay, what is this h bar? H bar is your reduced Planck's constant, which is defined by h bar is equal to h by 2 pi. Okay, and since the curvature of this A curve was sharper compared to this curve B, so what we concluded was the inverse, the effective mass of A, right? Effective mass corresponding to curve A was less compared to the effective mass corresponding to curve B. Okay, so since we were asked to find which one has the heavier electron effective mass, so we concluded that the band B has heavier electron effective mass. Is this question clear? Should we move ahead? So let me do one thing. Uh, I'll be moving ahead without stopping, and wherever you have any doubt, you can stop me, okay? And then accordingly, I'll address it out. Uh, okay. So now the second one. Second one was the definition of the Brilliant Zone, which is a simple question, and I won't be discussing that uh, in this session. The definition for the Brilliant Zone would be a region of K space that would contain all the unique solutions of the wave equations, right? And this is the reduced and the extended this Brilliant Zone diagrams, right? And then we have question number three, in which we had to consider a semiconductor, right, whose energy dispersion relation EK for the conduction band is defined by this. E is equal to A plus B times K minus C square, right, where your A, B, and C are constants. Assuming that the mobility of electron is mu naught, we had to find the mean free time of electrons in the conduction band. Okay, so how did we proceed on this one was firstly, see your mu naught is q tau by m star. You must be knowing this particular formula, right? And from this one, we, we can rearrange this equation to obtain this that your mean free time, uh, your tau, is equal to m star mu naught by q, where your m star is what? Electron effective mass, right? And your mu naught is your this mobility. Yeah. Uh, do you have any doubt?
No, sir, please carry on.
Okay, 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 okay. So this is your tau, right? And in tau, this and this particular, see, you were already asked in the question that you can assume that your electron mobility is mu naught. So I can say that this mu naught and q are not unknowns, these are knowns. But what about this m star? This is not known, right? But we can find this using this particular formula, right? Because we have been given EK relation and we know that m star is related to your curvature by this particular formula, right? So what we'll do is we'll differentiate this E versus K relation twice to obtain this. Okay, your E was A plus, oh, sorry, your E was this, right? And if you differentiate it twice, you'll get that dou 2E by dou K square is 2B, right? So then your effective mass m star would be h bar square by this, right? 2B. So this is h bar square by 2B. And once you plug in this here, you obtain this. Is this clear?
Sir,
Yeah.
uh, it is clear, sir, but sir, I am joined a little bit of late due to internet issue. Please see the this is the first problem.
No, we started with this problem. This was, in fact, the easiest one. I mean, in fact, we already used this in problem number three. So this we
Okay,
can
sir.
say
Sir,
is kind of a repetition. So
so
should I
it
repeat
is
this problem as well?
yes, sir. From beginning, sir. It is beneficial for us.
Okay, okay. See, we were given two curves, right? Your we had two EK curves, the solid line EK curve and this dashed line EK curve. Okay, and we had to comment as to which one among these two curves would correspond to heavier, like heavier this electron effective mass. Okay, so uh, we know that the curvature in this EK, right, is related to your effective mass by this particular formula, isn't it? So dou 2E by dou K square for this curvature A, which among these two curves has more curvature? I mean, which has a sharper curvature? It's curve A. Do you agree?
Yes, sir.
Right. So I can write this that curvature for A is greater than curvature for B, right? So if that is the case, I know my effective mass is inversely proportional to curvature. So I can conclude that effective mass of A is less than effective mass for B, right? So I can conclude that band B has heavier electron effective mass. Is
Yes,
this
sir.
clear?
Yes, sir.
The second one was definition. I mean, it was a MCQ definition based. I skipped this. It simply states that Brillouin zone is a region of K space that contains all the unique solutions of the wave equation, and the other options did not make sense, or I should say, were not appropriate. Okay.
Sir, sir,
So
in
yeah,
in that curve, third page.
third one. Wait, this one,
No, before that,
this one.
yes, yes. In this
Yeah,
case, the first curve is called blue curve is called Brillouin zone, na?
that is your first Brillouin zone. Yeah, this one is your
Yes, yes.
first Brillouin zone. This is your second, and this is your third. That is how.
No, for sir, any kind of semiconductor, we are consider only first Brillouin zone for
For
calculation
any
simplicity.
semiconductor, we
For
consider first
calculation,
Brillouin zone. Why
for
do you
cal
say so?
for calculation simplicity, sir,
For calculation simplicity.
and maximum electrons are placed in that particular first Brillouin zone, sir.
Your maximum electrons are placed in the first Brillouin zone. Mm,
Sir, actually, uh, sir told that for
uh-huh.
sir in a lecture videos told that we are consider only the first Brillouin zone for our calculation simplicity, as well as maximum allocation will be stay at that particular location.
Okay. Uh, are you talking about this? I mean, what we do is if this is the extended representation of your Brillouin zones, this is your this, what should I say? The reduced representation in which we utilize the periodicity of C. These are periodic with period 2 pi by A. Do you agree?
Yes, sir. Yes, sir. Yes, sir.
So I can shift this by 2 pi by A. And if I do so, this will come here. Similarly, I can shift this here. This will come here. So I mean, these two are equivalent. Would you agree with that?
Yes, sir. Yes, sir.
I guess you are probably referring to this. We usually use this kind of representation over this. Is
Okay,
that
sir.
clear?
Okay. Okay, sir.
Okay. So we'll move ahead. Question number. We can talk on mail as well. If you still think this your question was not addressed, you can drop me an email and I'll try to understand that and answer it accordingly.
Okay,
Uh,
okay. Sir, this problem again
oh,
one more time. Just for formula, sir. I'm
this one.
yes, yes, yes.
Okay. See, your we what we had to do in this question is you had to consider a semiconductor whose EK relation for the conduction band was defined by E is equal to A plus B times K minus C whole square, right? So your EK relation is given in this question, and you have been asked that your mobility. You can assume that your mobility is mu naught. Okay, you need to find the mean free time of electrons in the conduction band. So a formula that you might have, uh, I guess, gone through or come across in this course is following that relates your mobility to the mean free time. That is mu naught is equal to q tau by m star. If I rearrange this, I'll get this. That tau is equal to m star mu naught by q. Now, mu naught we were asked to assume, right? Mobility of electrons, it was asked that you can assume it to be mu naught. Q is already known, right? So the only unknown left in this is M star, but we were given EK relation. So what we can do is from this particular formula that we had already used in question number one, we can write M star is H bar square by dou 2 E by dou K square, right? So
Yes.
if, yeah,
Okay, sir. No issue.
okay. So now I'm using this EK relation here. A plus B times K minus C square. So if I differentiate it with respect to K, I'll get 2B times K minus C. If I again differentiate it, I'll get 2B. So I'll replace this by 2B. So my effective mass would become this, right? Effective mass would be H bar square by 2B, right?
Yes,
And
sir. Yes, sir.
if I substitute this in in place of this in this equation, my mean free this time of electrons in the conduction band would be h bar square mu naught by 2bq, right?
Yes,
So
sir.
this
Clear.
was your question number third. Let's quickly move on to the fourth because we'll try to finish as many questions as possible today. The question number four stated that uh, consider the following energy dispersion relation for a charge carrier in a periodic crystal lattice. Your E of k is equal to 2 sine square of k, right? The expression for the effective mass m star is simply, I mean, we were given EK relation. Again, I'll different, see what I'll do is I can write this as this, right? How so? My this cos of 2k is this. I guess you already know this, right? Cos of 2k is 1 minus 2 sine square k. If I utilize that, I can write this as this, right? And then if I were to differentiate this two times, I'll obtain this. Dou 2 e by dou k square is 4 times cos of 2k. Okay. Then my
Yes,
effective
sir.
mass is simply h bar square by dou 2 e by dou k square. This is simply a mathematical problem. I mean, the reason why I had put this problem was to show you, to make you comfortable for to use these EK relations for the effective masses. Okay, so that's how you compute expression for the effective mass in this question, and it comes about as h bar square by 4 times cos of 2k. Okay. Now, uh, next question was that assuming the silicon band gap as 1.12 electron volt at the room temperature, with the Fermi level located exactly in the middle of the band gap, you have to answer the following questions, right? Should I repeat this as well, or are you comfortable in this? I mean, you can go through the
Sir,
solution first. If you think, uh, mm,
sir,
I mean, there is need for me to repeat it, I'll repeat it. Yeah.
sir, you provide two questions which are not solved by you.
Did
Assignment
I?
questions.
Yeah, assignment questions. So did you try them out?
Sir, I try, sir.
Okay.
This one, but sir, I have not get answer.
You did not get answer. I would be interested in seeing that solution. Do one thing, do mail me the solutions, okay?
Okay, sir,
And
okay. Today
also,
I
I
mail
mean,
you, sir.
okay, this homework problem one and homework problem two, where I mean, they were way difficult than uh, the average difficulty of this course. So even if you are not able to solve this and this, don't be discouraged. I mean, okay, the problems, the difficulty level of the problems would be way less than these two. Okay, these problems were meant for motivated students. Okay, that's why I had
Okay.
kept them. Okay,
Then, sir, you
so
just explain the first two, sir.
first two, which first two? Just a second. You mean this one, fifth?
No. This 5 and 6, sir.
Yeah, this one, right? Fifth.
Okay. Yes,
Okay.
sir. This. It can
Yeah.
be recapped, sir,
So
one more time, sir.
yeah, I got it. So assuming the silicon band gap at room temperature is 1.12 electron volt, with the Fermi level located exactly in the middle of the band gap, you need to answer the following question. Just a second. Okay. So what is the probability that the state located at the bottom of the conduction band is filled? So as I had elaborated at uh, the week one live session, what gives you the probability that the state is occupied at any energy E?
Sir,
That is this, right? F of E, right?
yes, sir.
And your F of E is given by this particular thing, right?
This
1
is the
by 1
Fermi Dirac
plus,
distribution.
yeah, that particular distribution. So if, so this is at any energy E, right? If I put E is equal
Yes,
to
sir.
EC, why? Because we are being asked about the probability of the state that is located at the bottom of the conduction band. So if I put E is equal to EC, my F of EC would be this. Do you agree?
Yes, sir.
Right. And I can approximately write this as this. right? Because I can assume that this particular thing is way greater than 1, right? And if I assume so, it would be approximately equal to exponential of minus EC minus EF by KT. Okay,
Okay, sir.
just a second. Fine. Now, also note that your Fermi level was located in the middle of the band gap, right? Your Fermi level was located in the middle of the band gap. So I can write EF is equal to EC plus EV by 2, right? So if I from this, if I yeah, from this I can write EC minus CF is equal to EC minus EC plus EV by 2. I just substituted EC plus EV by 2 instead of EF, right? I can simplify this to obtain EC minus EV by 2, right? If you simplify this, you'll obtain this EC minus EV by 2, which is nothing but your EG by 2, right? So in other words, this factor EC minus EF can be replaced by EG by 2. Okay.
Okay, sir.
Okay, what else should I show? Just a second. Okay, then we had to give a numerical approximate of this, right? So, okay, this is your f of EC. This is your f of EC. If you don't take the approximation, okay, if I don't take this approximation, I only consider this and I put in the values, right? I have been given this 1.12 temperature. I don't need anything else, right? Since it's room temperature, my KBT would be 0.026 electron volt, right? And if you compute the value of EG by 2 KT, that would be 21.5, right? It would be 21.5. Notice this, the value 21.5, and this goes in exponential, right? This 21.5 comes in exponential. So exponential when when this Euler's constant E is raised to the power 21.5, that is a very large number compared to 1, right? That is also one more reason why this approximation makes more sense. Okay, now this is the value when no approximation is taken. In fact, one of the students at that time in the session calculated it using the calculator. It came out as 4.43 into 10 to the power minus 10. Okay, and if we use the approximation, so I'm distinguishing this f of EC from this f of EC naught. What is this f of EC naught? This f of EC naught is when this approximation is used. We also call this as non-degenerate approximation. Okay, if you use this non-degenerate approximation, what is non-degenerate approximation, by the way? What is, uh, I mean, how do we know if it's non-degenerately doped or not?
Well,
Suppose I don't give you the location of the Fermi level, right? And tell you to comment what would be the solution in general. And then I ask you, when would you use this non-degenerate approximation? So is there any particular limit? Firstly, what do you think would determine if its semiconductor is degenerately doped or non-degenerately doped?
sir, actually, sir, the Fermi level locate
Uh,
very near to the conduction band or very near to the valence band is called non-degenerative.
that is degenerate doping. That is degenerating doping. The more it is far away from that, so it turns out that you were
Yes,
right.
yes.
See, if the difference of conduction band edge or say valence band edge and Fermi level, if you take difference of these two, if that is greater or equal to 3 kT, right? If it's
Yes, sir. Yes,
greater
sir.
than 3 kT, that is your non-degenerate approximation. Okay, here it was greater than 3 kT because see, it was located in the middle, right? This was your EF, right? See, the Fermi level is located exactly in the middle of the band gap. And middle of the band gap is, see, let's take an estimate. See, what is KT?
Of 0.026, obviously 0.078.
right? So it's 0.078. And what is half?
1.12, half of 1.12,
Half
half
of
of
1.12 is way greater than
1.6.
0.075, roughly,
Yes, sir. Yes, sir.
right? So that's why we can use non-degenerate approximation in this case. Fine.
Okay, sir. Okay.
So now you know when to use non-degenerate approximation and when to not use it. Okay. So what should I else teach? Okay. Then was part B. What is the probability that a state located at the top of the valence band is empty? Okay. What is the probability that a state at, okay. So the probability that a state is empty is equal to 1 minus probability that the state is occupied, right? In other words, it would be 1 minus f of v, the way we defined f of v, right? Because there are only two possible events. Either the state would be filled or the state would be empty. I mean,
Yes,
it
sir.
cannot be partially filled. I mean, either the
Yes,
state is empty or the state is filled, nothing else. That is the sample space for
sir.
this. Oh, yeah,
Sir, I have a question, sir.
yeah.
Sir, in case of non-degenerative condition,
Non-degenerately doping, yeah.
doping, the equation will be that particular e to the power minus.
I mean, see, this is valid in general, okay, for non-degenerate as well as degenerate. It's just that for non-degenerate approximation, this whole equation simplifies to this. You
Okay, sir.
cannot
Okay.
use this. You cannot use this if your Fermi level is too close to the band edge.
Yes,
If
sir.
it's
Yes.
too close to the band edge, when will the Fermi level be very close to the band edge?
Sir, interdoping, sir. Either P type or
When the
interdoping.
doping is very high. Okay,
Yes, sir.
so
Yes.
you need to take care. When the doping is very high, you cannot use this. You have to use this. If the
Okay, sir.
doping is, I mean, I mean, if the doping is enough or sufficiently in our desired way, so then you can use this, right?
Okay, sir.
It should
Okay.
not be that high. The idea is that. I think you got the idea, right?
Yes, sir. Yes, sir.
Okay. So where was I? Okay, now coming to this one.
Empty, sir. Band is
Yeah.
empty.
So as I said, a state can either be empty or it can be filled. I mean, there is no other possibility. Or if you can think of any other possibility, you can say, right? There is no other possibility, right? Either your state is filled or your state is empty. And also, we know that the total probability is always one, right?
Yes, sir.
So, if we say the probability that the state is filled, that probability is given by f of v, then the probability that the state is not filled would be 1 minus this probability, since the total probability has to be 1, right? So that is what I used.
Yes.
F of E is this, and 1 minus f of E is that the probability the state E is empty. So if your f of E was this, right, and in this question, your E would be EV, right, top of the valence band. So if I put that E is equal to EV in this, so this would be my required probability. What would this be? This would be the probability that the state is the top of the valence band state is empty, right? This would precisely be this probability. So if I
Yes,
put
sir.
in the values, again, this EV minus EF would be minus EG by 2, right? Because this is your Fermi level, this is your EV. You're subtracting this from this. Sorry, you're subtracting Fermi level from this. So it's expected that this would be a negative one.
Negative.
So
Negative.
that's why we get this and this. And yeah, and if you proceed to simplify this, you'll conclude that 1 minus f of EV would be 4.43 to 10 to the power minus 10. Is that fine?
Yes, sir. Fine, sir.
Okay. So now what? Now, then we had question number 6. Right. In question number 6, for silicon at the room temperature, we had to calculate the following quantities. Right. The density of states in the conduction band, GC of V, at energy 26 millielectron volt above the EC. So this was the expression that I used. Probably you might have seen a different expression of GC of V, but they both are equivalent. If you use suitable substitutions, you'll get to this expression. Okay, it could be that you had used Planck's constant instead of reduced Planck's constant or something similar to these things. But this is dimensionally what you will get for GC of E. What is this? This is density of states in the conduction band. Okay, GC of E. And this is valid for E greater than EC. Here h bar is h by 2 pi. Okay, I can write this, right? What I did is I divided by this m naught raised to the power 3 by 2 and I multiply by m naught raised to the power 3 by 2. This is m naught and square root of m naught, which is m naught raised to the power 3 by 2, right? Is this fine?
Sir.
Yeah.
Yes, sir. Okay, sir. You can just adjust the root over part.
Yeah, that's what I'm saying. I'm writing this m naught raised to the power 3 by 2 in the numerator as m naught square root of m naught, which is nothing but m naught raised to the power 3 by 2. Fine. So this is fine. So now what I do is I plug in the values. I know my rest mass is 9.1 into 10 to the power minus 31. Yeah, I should write kg, okay. And pi I'm taking as 3.14. My reduced Planck's constant is 1.06 into 10 to the power minus 34. If you don't remember the value of the reduced Planck's constant, what you can do is Planck's constant, I'm assuming you would be knowing the value of the Planck's constant. And if you divide that by 2 pi, you'll obtain this, okay? What is the value of the Planck's constant, by the way?
6.2 into 10 to the power minus 23.
6.36. Probably it's 6.36 into 10 to the power minus 34 joule second. Do remember the values. I mean, these numerical constants would come in handy. Okay, please try to remember them. Planck's constant is one such. Okay, then if you plug in the values, this is what you'll get. Your GC of E would be 1.35 into 10 to the power 56 square root of E minus EC. And this would be the unit, right? Joule meter cube inverse, whole inverse. So now for this question, this E minus EC would be 26 milli electron volt. Why? Because it is said that the energy E is at an energy 26 millivolt, 26 milli electron volt above EC. That's why I can write E minus EC as 26. Is this fine?
Okay. Yes, sir.
Okay. And so that means if I convert it into SI, then this is what I'll get. Right? I have to just multiply this by the charge, electron charge. So E minus EC would be this. Then what? Then I'll replace this E. What have I done? Okay. See, if E minus EC is 26 milli electron, what is E? EC plus 26 milli electron volt, right? That is what I'm doing. I'm replacing E by 0.026 plus EC. Fine. This particular, that is equal to, and just plug in the value. This is plug and play, nothing. Okay. And similarly, you can do for this GV of E, valence band.
Okay, sir.
Okay. So part A and part B.
In that case, I have to put the EV minus E.
Yeah. In that case, you have to put EV minus E. See, here it's given that your energy E is 26 millielectron volt below EV, right? So E minus EV, sorry, it would be EV minus E. That would be what? 26 millielectron volt.
26. Okay.
And accordingly, you will proceed like we did, right? I mean, I had already shown this part, right? You might be needing this particular ratio, right? And we used this Mn star by M naught here. Here, you will use this MP star by M naught. Okay, then part C, right? Sorry?
Yes, sir, for third.
Yeah, for third part. Just a second. For third, the effective density of the conduction band states NC, right? What is NC? So the expression for the NC would be the expression for the NC. This is this is for a particular case. This would be the expression for the NC. It's not, it's not expected that you would remember this formula, but say suppose this is given to you, then you can utilize this ratio, right? Mn star by M naught, that is 1.18, And if you use that in this, then your NC can be computed, right? And NC comes out as 3.22 into 10 to the power 19 per centimeter cube. And similarly, if I give you this particular formula, you can utilize this ratio and compute NV. Then NC by NSI. What is NSI?
Atomic density of silicon.
Yeah, and what is atomic density of silicon? How many atoms are there in 1 centimeter cube?
Yes, sir.
This is a constant that you are supposed to know. Okay. Even in this,
9.1, sir.
no, no, no. It's 5 into 10 to the power 22. At least remember the order.
Yes,
There
yes,
are
yes.
10 to the
Yes,
power
sir.
22 atoms of silicon in 1 centimeter cube. Okay. In 1 centimeter cube volume. So this order you should be able to have an idea of. I mean, do remember this. Okay. Memorize this. 5 into 10 to the
Okay,
power
sir.
22. This is optional, but the order is something that you are supposed to know at this stage. So then NC by NSI is simply the ratio of this and this that we know. And if you take the ratio, it comes about as 6.44 into 10 to the power minus 4. If you convert it into percentage, that is nothing but 0.06 percentage. Okay.
Okay, sir.
So yeah, that finishes your week one, right? Let me do one thing. I'll take a 5 minutes rest. Okay. I mean, that was a little intense mini session. I'll take a 5 minutes rest and then I'll start week two. Okay.
Okay, sir. Okay, no issues.
Okay. Just give me a couple of minutes or 5 minutes. Yeah, so thanks. Sorry for the long break. Now let's see where we are. Just a second. So now it's week 2, right? So in week 2, the topics uh, that were covered were following: doping and intrinsic carrier concentration, the equilibrium carrier concentration, this temperature dependence of the carrier concentration, high doping effects, and incomplete ionization. Now, this was the first question, right? We had to consider silicon at room temperature, and for each of the following cases, we had to calculate what? Equilibrium electron. So we had to compute the equilibrium electron and hole concentrations, NP and N and P, right? And we had to assume what? That we have fully ionized dopants. Now, for the first one, when we have an intrinsic material, both ND and Na are equal to 0, right? And in that case, what would be our N and P be equal to?
Ni square.
Yeah, NP would be Ni square. But what would be N? What would be P?
Na by Na. I think Na and is 0, na?
Yeah,
Na by
see, these are 0.
0, sir. Then
Won't,
0.
won't both be Ni? Since you said NP is Ni square and we are not doping,
Yes,
so both are equal. So the only way it would be satisfied is when N is equal to P is equal to Ni, isn't it?
yes, sir. Yes.
And let's take Ni as 10 to the power 10 per centimeter cube. It's probably 1.5 into 10 to the power 10 centimeter cube, but let's simplify the matters and keep it 10 to the power 10. Okay. Now, what for this now? Part B. Firstly, tell me one thing. What is this semiconductor type?
N type, sir. N type.
N type. Reason is because we are using donor doping, right?
Yes, sir.
Since we are using donor dopants, so your ND is 10 to the power 13, and we are not using acceptor ions, right? So now see, our N would be Ni plus
Ni
ND,
plus NT.
right? Which is approximately equal to ND. Why? Because 10 to the power 13 is way larger than 10 to the power 10, isn't it?
Yes, sir.
So that's why I
Power
can
of 3,
write,
sir.
yeah, order of 3 is a lot
Order of
because
3.
your Ni by ND, it's 1 by 10 to the power 3. That is a lot, right? So that's why I can directly write N as ND, and then my ND is 10 to the power 13. So that means my N is 10 to the power 13. Then how do I compute P? P is simply Ni
N,
square by,
N equal to Ni square by ND.
yeah, NP is Ni square, and your N is ND. So your P is Ni square by ND. So do remember what we did. We first computed N, right? In N-type semiconductor. And then we proceeded to compute P. P was minority carrier here. N was majority carrier here. So do keep this recipe in the back of your mind. Now, when let's see, what should I take? I'll take this problem now. I'll take this problem, okay? Problem D first. In problem D,
Same,
what was the,
same,
see,
sir.
it was P type, right? It's P type since we are only using acceptor ions, right? Now,
Yes.
since it's P type, which concentration would I first compute? Which equilibrium concentration would I first compute? I'll compute
P, sir.
P,
P. P, then
right?
put the value of P then.
Right. And P is Ni plus Na. And see, the difference is order of 7, right? 10 to the power 10. Ni is 10 to the power 10. Na is 10 to the power 17. So the difference is around 10 to the power 7 order difference. So that's why P would simply be Na, which is 10 to the power 17. And my N would be Ni square by Na, right? And it's 10 to the power 3 per centimeter cube. Now let's consider this one. Uh, just a second. C part, right? In C part, my ND was 10 to the power 17 per centimeter cube, obviously. And Na was 0,
0.
right? Yeah.
N type,
Uh,
sir. N type.
Yeah, this is N type, obviously, and we are doping it way high, right?
N plus type.
Yeah,
N plus type.
yeah, correct. So N would be 10 to the power 17, right? And your P would be 10 to the power 3, right? Simple. I mean, problem B and problem C were similar. Now comes problem which E, right? We already discussed D. So now it's E. E has both types, right? We have both ND and Na. And as I said, the recipe that's to keep in mind is start with the majority carrier. ND is 10 to the power 17. Na is 3 to 10 to the power 17. So which does dominate? Na dominates, right? So the semiconductor would primarily be P type.
P type.
Right? So what I'll do is I'll write net p-type doping. That would be Na minus Nd. That would be 2 into 10 to the power 17. Why am I not writing Ni? Because Ni is way negligible in this order, right? 10 to the power, Ni is 10 to the power 10. This is 10 to the power 17. So adding that or subtracting that hardly makes any difference, right? It's actually, yeah, do keep that in mind. So your N would be what? Ni square by this, 2 into 10 to the power
N
17.
minus ND.
Yeah. And then if you calculate that, that comes about as 0.5 into 10 to the power 3 per centimeter cube. Okay. So now, then we have question number 2. And in question number 2, for each of the cases in the problems, we need to compute what formula. See, let's do one thing. We'll discuss these questions superficially. If we discuss them in detail, then I mean, I don't think we'll be able to touch today's session. So I'll be moving over superficially. If you have any doubt, you can stop me and I'll try to explain that. Is that fine?
Okay, sir. Okay.
Because it's already 15 minutes and we are only at week 2. So we are lagging right now. That's why. So now we need to compute the Fermi level position, right? For first one, it's simple because for an intrinsic material, your EF will coincides with EI, right? So EF minus EI is 0 and we got the location. And for the subsequent questions, I'll utilize these two formulas. Okay, I'll utilize these two formulas to compute what? EF minus CI and EI minus EF, right? Because N and P are known for each of these cases. Why? Because I computed all of them in question number 1. Fine. I'll substitute them and get the answer. So you can do that and verify it. Now question number 3. For each of the cases, case A to E, what you have been asked is, uh, okay, for the cases A to E in problem 1, you need to calculate the Fermi level position with respect to the bottom of the conduction band. Okay, EF minus EC is what you need to compute. Note that you need to consider the sign. Okay. So my N is this, right? NC exponential of EF minus EC by KT. And what? Uh, yeah, I mean, I'll utilize this formula and compute what? EF minus EC. Because N, I know this is a constant that you can use, and that's it. Do remember the order. I mean, this will come in handy. Remember the order of NC. What is the order of this? What is this? Effective conduction band density of states. Okay, so this has an order 10 to the power 19. We saw this in week 1. Okay, how, what was the formula in general? I mean, this is for silicon, I believe. If the material is not silicon, then the ratio of the effective mass to the rest mass would be different. And you need to plug into that equation that I had showed. If you want me, I can show you again. This was that formula, right? And we had computed this, right? This ratio
Sir,
holds good for, yeah.
sir, how can we mark up this particular formula, sir? Because this is
Probably,
2.51 into a 90.
yeah, you're right. I mean, no need to mug up this formula for the sake of this course, but do remember one thing that your NC, the order of your NC is 10 to the power
Into
19 in
90.
silicon. Okay, this is simple, right? You can remember this 10 to the power 19 per centimeter cube. That's the order of what? Conduction band density of states. Similarly, the order of the valence band density of states is 10 to the power 19 as well. So it's one number that you need to keep in mind, 10 to the power 19 for both the density of the states, effective density of the states. Okay. Coming back to the question. Okay, this can be now done, right? Now let's move on to the question 4. Assuming silicon with completely ionized dopants, compute N and P for the following. Now you are given ND, right? Now your Ni is changed. See, up till now, what was your Ni? 10 to the power 10. But this is a temperature of 700 Kelvin, right? And I'm giving you this info. Okay. At 700 Kelvin, your Ni is 2.865 into 10 to the power 16. So if that is the case, can I neglect Ni when ND is used?
No, sir, no.
Because they are comparable, right? This is 10 to the power 16, this is 10 to the power 16. So I can no longer neglect Ni. I have to consider Ni in my calculations. So that is how I'll use, right? So this is the charge neutrality equation, right? Your P minus N plus ND plus minus Na minus is equal to 0, right? These are free charges and these are fixed charges, right? So now this is 0, right? Okay, first I'm showing, okay, what I'm doing is here Na was 0, but what if Na wouldn't have been 0? Suppose there would have been a value of Na as well. So let me show the procedure for that general case. So you'll write this equation. Why I'm replacing this by this? Because I have completely ionized dopants. When I
Yes,
have
sir. Complete
completely
right.
ionized dopants, then my Nd plus is Nd, right? All of them are ionized.
Yes.
So I can write this, right? What I'm doing here is, see, in this case, it's Nd, right? So what will I compute first? Majority carrier, right? N. Remember the recipe?
Majority. In.
We go for the
Yes,
majority
sir.
carrier.
Yes. Nice,
So I'll
sir.
go for the majority carrier.
Nice,
I'll
sir.
convert everything in terms of N. I'll write everything in terms of N. So my P is Ni square by N minus N plus Nd minus N is equal to 0. Okay. So if you rearrange and simplify, you'll get this equation. Okay. If you write the solution of this quadratic equation in terms of N, okay, if N is the variable of interest, remember, I mean, this is, you can treat this as a constant. I'm interested in N. So if I, this is quadratic in N. So if you solve it for N, you'll get this, right? And upon rearranging, this is the particular solution that you get. Here I have taken Na is 0 because that was what was said in the question. If Na wouldn't have been 0 in the question, you can still compute it from this relation, right? This is general. Is it fine? Fine,
Yes,
right?
sir.
Write this, right? Okay. This was from this, and this is the solution of N that you get. And if you I guess plug in the values, your N would be this, and P would simply be Ni square by N, which is this. Is this fine now?
Okay, sir.
Okay. Was I audible?
Okay. Yes, sir. You're audible.
Okay, fine then. So now, okay, next problem. Okay. So the next problem is following. For the case of the problem 4, you need to calculate the Fermi level position with respect to the intrinsic level, EF minus EI. What I'll do this, I mean, I'll utilize these formulas, right? And I know N and P. Do I know them? I've computed them, right?
Yes, sir.
I'll utilize these and use these formulas to compute EF minus EI. Is that fine?
Sir, KT by Q is given. Yes,
KT
yes.
by
In
Q
the
is
previous
given.
problem.
See, you know the temperature, right? Temperature is 700 Kelvin. Then KT by Q can be
Okay, right.
computed, assuming you know the
Okay.
Boltzmann constant. Yeah, one more thing. You need to remember the Boltzmann constant as well. So do, uh, what should I say? Do remember the value of the Boltzmann constant as well. Memorize that as well. Okay. Boltzmann constant is fundamental unit, at least in this course. So you are supposed to know that. Okay.
Okay.
So usually KT by Q is 0.026 electron volt, but
Yes.
here Here temperature was different, right? Temperature is different, and that's why this zero, we get the value 0.0604 electron volt, and that's the reason our Ni was given, right? Ni in this question was given. And yeah, so EF minus EI turns out this is this, so that is around 0.048 electron volt. Okay, EF minus EI. So that was the question. Again, homework problem 1 and homework problem 2 were optional. Good if you solved them. If not, we can discuss via mail. Okay, you can mail me the solutions and I'll see if you have done it correctly or not. Okay, let's move on to the week 3. So we took around 1 hour for the 2 sessions. We need to move faster. So now we have carrier scattering and mobility, low field and high field transport, introduction to diffusion, drift diffusion and trap statistics, current continuity equation, and introduction to the PN junction. Okay. So this was the problem, right? So we had to assume that in a given semiconductor, there is only one scattering mechanism present, right? And it has a relaxation time of 0.2 picoseconds. Now determine the electron mobility in this sample. So how do you compute mobility given this relaxation time? You use the formula Q tau by m star. Once you use that, your mobility comes about as 703.3 centimeters square per volt second. Now this is corresponding to scattering mechanism 1. The question then proceeds, right? It says now if there were another scattering mechanism with a relaxation time of 0.3 picoseconds. Okay, so now I have another scattering mechanism of relaxation time 0.3 picoseconds. I'll use again this formula and compute the mobility, which comes about as 1054.9 centimeters square per volt second. Now it's saying that what is the overall electron mobility in the sample if both the scattering events were present simultaneously. Okay, now if both of the scattering mechanisms, if more than one scattering mechanisms are present, we utilize or make use of Matheson's rule. I assume you would have gone through that rule, right? You can either see or visualize that rule in terms of mobility, or you can visualize that in terms of this mean free time.
Time
Okay.
constant.
Yeah, time constant, or I should say relaxation time, whatever. So now it turns out that your see, this one way to do this would be to write 1 by mu is 1 by mu 1 plus 1 by mu 2 and then compute mu net. That comes about as 421.98 centimeters square per volt second. Another method is to first compute what is the net relaxation time. Your net relaxation time would follow the same rule. 1 by tau net is equal to 1 by tau 1 plus 1 by tau 2, and you'll compute tau net. Once you obtain tau net, then compute mu net by plugging the tau net value in this equation. Okay, write Q tau net by Mn star. Once you use that, you'll find the answer. Is it fine? Also, I used one thing here. I had to assume Mn star is 0.5 times M naught. That is what I had used here and here. Okay, this is 0.5 times M star. M naught is what? M naught is your rest mass.
9.1.
Yeah, and you need to remember this constant as well. M naught is something that you should know. So the rest mass of an electron is 9.1 into 10 to the power minus 31 kg. Okay, this is something that you're supposed to know. So do memorize this constant as well. Okay.
Sir, kindly tell the formula, sir, to calculate
Formula for what?
net mobility. To calculate
Formula
the net
for what?
mobility. The name of the formula, sir, which you told, sir.
Okay, this one. This is Matheson's rule. You can search it up. Matheson. Was this not taught in the course? I guess this would have been taught in the course. Was it?
Yes, the thought.
This
I
would have been.
forget, sir.
Yeah, write this. Matheson. You can search it on internet there. Matheson's rule, something like this. Okay, this is the formula. I mean, sorry, this is the name of the rule. You can write it. So now what? Then we have question number 2, which is to this. Okay, now you can assume a bulk N-type semiconductor with mobility 1000 centimeters square per volt second. Okay, fine.
Okay.
Now if the electric field is what? 100 volts per centimeter, right? Ex is 100 volts per centimeter. What is the sign and the numerical value of the electron drift velocity? So this is the electron drift velocity, and that is equal to minus mu n times electric field, right? What is mu n? 1000. What is
Mobility.
Ex? That is 100, right? Please note the sign. Why would this be negative? Because your drift velocity of the electrons would be opposite to the direction of what? electric field, right? Because
Diffusion.
electrons drift in the
Yes.
direction that is opposite to the electric field. That's why I put a negative sign over here. So it turns out your drift velocity of the electrons would be minus 10 to the power 5 centimeter square per second. Okay. And now we have question number 3, which was as follows. Okay. So a p-type silicon sample with Na this. Okay. We were given optical generation rate and we were supposed to assume 100% ionization. Tau n and tau p was 5 microseconds. Uh, okay. Ni, we had to take 1.5 into 10 to the power 10 per centimeter cube. Firstly, I had to determine electron and hole concentrations N and P respectively and the percent change from their equilibrium concentrations. So my equilibrium, first I'll compute the equilibrium concentrations, right? My equilibrium concentrations would be, again, I'll first compute the majority one. So my P naught, since it was doped with Na, my P naught would be 10 to the power 15. Then I'll compute the minority one. My N naught would be Ni square by P naught, right? Which is 2.25 into 10 to the power 5 per centimeter cube, right?
Okay, sir.
Now, what about this? This is the excess holes generated, right? This is given by optical generation rate times this time constant, okay, tau p. Similarly, excess holes generated would be given by gop times tau n, and the value would be same because your tau n and tau p is same. So the both value comes about as 5 into 10 to the power 12 per centimeter cube. Okay, so these are excess holes and excess electrons. So now what would be the total or net electron and hole concentrations? It would be simply the sum of this equilibrium and this excess, right? So it's P naught by plus delta P. Similarly, N naught plus delta N. And since you're this, here P naught was way greater compared to delta P, right? See, this is 10 to the power 12. This is 10 to the power 15, which is way greater. So my P naught plus delta P would be P naught, right? Which is 10 to the power 15%. But in case of electrons, my N naught, it was 10 to the power 5.
Is the
Yeah.
is the optical recombination is given, sir?
Optical generation rate is given. It's 10 to the power 12.
Okay,
Right?
okay,
I'm
okay, sir.
using that here. Using that here.
Okay, 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 okay.
Yeah.
Then, sir, then you add the excess carrier with the actual carrier.
Yeah, that's what precisely I did. Okay. Then once you do that, notice here n naught plus n. Here n naught was 10 to the power 5. Here delta n is 10 to the power 12. And delta n is way greater than n naught, right? So this is n is delta n here, right? Here p was p naught, right? So then you calculate the percentage change. Here it was 0. Here it's around 2.22 into 10 to the power 9%, right? This so the key idea or conclusion was that minority carrier concentration changed significantly in optical generation process, right? So
Yes, sir.
what else? Yeah.
1 minute, sir. 1 minute, sir.
Yeah.
Sir, in that case, your P naught is 10 to the power 15 order, and delta P is 10 to the 12 order.
Huh.
So you put the value of P minus P naught.
I mean, I'll compare this, right? I'll compare this with this. Both are 10 to the power 15, so both are 0. That's why 0%. Is this fine?
Okay, in that case, 5 and 12. In that case, in case 5 and 12. That's why. Okay. Okay, sir.
See, this is 5 into 10 to the power 12. P neglects this.
No,
right?
no, I say that in case of n case, n
Yeah.
naught will be 10 to the power 5 and n will be 10 to the power 12. So there will be 2.22 into 10 to the 9.
Yeah, here
Okay.
n would be 5 to 10 to the power 12 and n naught was 10 to the power 5. So there is significant order, right?
Okay.
And if you divide that by n naught and multiply by 100, it turns out that the percentage is 2.22 to 10 to the power 9%. You can verify that as well, okay?
Okay.
So now my NP, what would be my NP? My NP would be 5 to 10 to the power 12 times 10 to the power 15. And if you see,
Yes,
it's greater than, way greater than Ni square, right? So what does that indicate? That the process, we have excess carriers, right? If your NP is greater than Ni square, that is excess carriers. I mean, obviously it's not equilibrium, right? Had this been equilibrium, your NP would be equal to Ni square, right? And then based on the relation. Is it is NP less than Ni square or is NP greater than Ni square? We conclude whether it's carrier deficit or carrier excess. Here NP is greater than Ni square. So this is carrier excess. Had this been the case, this would have been carrier deficit. So now this is carrier excess. Now what else now? So E minus CF. Rest of the things you can tune to the week 3 video as well. Okay, to see what we discussed there. So now this problem I'll be skipping. I discussed this in detail in that session. Uh, okay, this one is simple. I mean, simple. Although, do you know what this relation is? dn by mu n is kt by q.
Yes, sir. Yes, I know that. Einstein's
This is
relation, sir. Einstein's relation.
Einstein's relation, correct. This is Einstein's relation. dn by mu n is kt by q. So now how would you compute dn by mu n at temperature 400 Kelvin? You'll compute kt by q first at 400 Kelvin, right? And mu
Yes, sir.
n
Yes, sir.
won't, then you'll, yeah, that's precisely the answer, right? Then dn by mu n can be computed. Right.
Sir,
Yeah.
can you explain the problem which you had literally discussed?
Which I
Probably not
discussed.
in there. Literally,
Which,
sir. You can keep the problem because you can discuss it. This problem.
which problem? This one? Question number 4?
4, 4, 4, 1, 2.
Okay, I'll
Yes,
discuss
it's
it.
a
No issue.
possible, sir. Last.
Okay, no issue, no issue. I'll discuss it. It's fine. I mean, this session is as per you. I mean, whatever you guys will say, I'll accordingly make this session custom to
Sir,
that.
if time
Yeah.
permits, sir, you can discuss, sir. Otherwise, last you can discuss.
We'll discuss this problem first and then see how much time is left. Okay. See, this is an intrinsic silicon sample is doped with a position dependent acceptor concentration. Na of x is equal to Na times, sorry, N naught times 1 plus x by L as shown in this particular figure. Okay. Fine.
Yes, sir.
Your N naught was 10 to the power 15 per centimeter cube and L was 5 micrometer. Fine. So you need to find an expression for E of x at equilibrium. So what fact did I utilize in solving this was at equilibrium, your current density is 0, right? Because there won't be current density flowing, right? Your drift component of the current density would be equal to the diffusion
Diffusion rate.
current density component, right?
No
So I'll
bending
write
is
the
there.
expression. Yeah, I'll write the expression for JP. Why I'm writing it for JP is because Na of x is given, right? Corresponding to Na of x, since it's given that, okay, just a second. I'll assume 100% ionization, okay? If I assume 100% ionization, then Na of x is precisely P of x, and that is equal to N naught times 1 plus x by L, right? So if I equate this to 0, what will I get? First, what would be the differentiation of this with respect to x? This derivative would come in handy later. If I differentiate this with respect to x, this would be n naught by L, right? This differentiation would be 0.
Yes,
N naught
sir.
x by L differentiation would be n naught by L. So this is understood. So now, if you rearrange this, you'll get this particular equation. Your electric field is dp by mu p by 1 by p of x dp of x by dx, right? Which is equal to kt by q. I'm using Einstein's relation for dp by mu. Okay, kt by q times 1 by P of x is what? P of x is n naught 1 plus x by L. I've substituted that. dp of x by dx is what? N naught by L. I'm substituting that here. Okay. And then if you see, there are few terms that will cancel out. Even L will cancel out here in the denominator, leaving L plus x here. So this E of x would be kt by qx plus L. Is this fine?
How the formula came, sir? E of x.
Which E of x, how did this came? There is E of x here, right?
Okay, substitute.
If you shift here and then divide this by this factor, you'll get this.
Okay, sir.
Okay, because q would anyway cancel out. You'll realize this if you do that on copy or paper.
Sir, why,
Okay,
sir? Why, sir? Because of, sir, the material are in equilibrium, JP equal to 0, na?
Yeah. Oh, this is valid only in equilibrium, that this current density is 0. The total current density is 0. Okay. At equilibrium, both your hole and electron current densities are zero. The reason
JP
I
and JN
took
are both are zero.
both are zero at equilibrium. The reason I took JP was because any of x was given. I was given the expression of p of x, so I could utilize that to compute e of x. Only that is only the reason that I took JP of x, because my purpose was being fulfilled in that. I did not know what would how any n of x would be, right? I did not know that. Um, Actually, that is one thing that you could explore. Okay, leave it. I mean, let's not complicate the problem. The problem is simple.
Okay, sir.
So
And the graph count.
yeah, now graph part. Now see, we had to evaluate then E of x at 0 and 5 micrometer. If you evaluate it at 0, then x is 0, right? This is kT by QL. Done. What about when x is 5 micrometer? Here L was 5 micrometer. So in other words, it's asking to compute E of x at L. If you compute E of x at L, here L plus L is 2L. So E of L would be kT by 2QL. Okay, now you know this particular formula that your electric field is related to the band profile, right? Whether it's EC, whether it's EI, whether it's EV. I discussed this in the last session as well, right? This particular formula. So 1 by Q dEI by dx. Here, it's not necessary that this would be EI. It can be EC. It can be EV. Why? Because they all track each other, right? See, they're tracking each other. Right. So usually we write this formula in terms of EI. That's why I have written it. There is no harm if you write it in terms of EC. And then accordingly, EI, EV would track them. Okay.
Okay, sir.
Yeah. Reason is, see, if I give you EC, say I give you EC profile, you know the band gap. Band gap is fixed constant, right? So EV has to track it. Are you getting the point?
No, sir.
Band gap cannot change. Band gap cannot change, right?
No,
If I
sir.
change
Whatever you
X,
told.
sorry.
Once more, sir.
Okay, see what
Whatever
I'm
you
telling
told
you.
the.
Yeah, I'm telling you, say I gave you the band profile of EC. EV has to track it. Why?
Yes, sir. Because
Because
the band profile, band gap will
this
be
will be
fixed.
constant throughout. Your band gap is a material constant. It cannot change with X. Okay.
Yes, sir. Yes, sir.
Okay, that is the reason why EC tracks EV. And why does EI track both of them? Because EI is technically the middle of them, right? This is EI.
Yes, sir.
So now we get the point why EC, EI, EV all track each other, right?
Okay, sir.
That is the reason I said you could use EI, you could use EC, you could use EV, anything here, any of the three. I use normally in books EI is what's used. Okay, DEI by DX. So now, okay, now you know what is E of X, electric field of X. What is E of X? This is 1 over F, 1 over X dependence, isn't it?
KT by Q.
KT by Q is there, obviously, but I have to comment on the nature of
1 over
electric
AC
field.
minus.
Right? This is
Inverse
reciprocal, 1
proportional
over
to
of X.
distance.
So what is a function which when differentiated gives reciprocal? It has to be
Minus 2
logarithmic.
order.
Logarithmic.
Logarithm. Yes.
You take the
Yes.
differentiation of log X, you will get
Yes.
1 over X. There is no other function that
Right.
has this property. That is why the EI will have a logarithmic dependence on X. Is this fine now?
Yes.
That's why the band
Yes.
profiles would be this, like this. Okay.
Okay, sir.
So now a quick question. In which direction would the electric field point? Would it be from left to right or right to left?
Sir, right to left.
Left to right. I already told you in the last session as well. Electric field always points in the direction in which the bands move upwards, right? So it has to point in this, which is also evident from this expression. This is a positive expression, right? And we are defining X to be positive in this direction. So if you would have judged from even this expression, the direction of the electric field was this. So now this is consistent even with this band profiles as well. Okay.
Okay.
Is this fine now? Now I'll move ahead. So now, okay, now it's 419. Okay. So let's do one thing now. Let's skip today's session. We'll discuss week 4 today. And in the next session, I'll discuss both week 11 and week 12. Will that be fine?
Yes, sir. Yes, sir.
Okay,
No,
I'll
no issue,
finish
sir.
week 4.
I think
Okay.
I don't know what about others.
Yeah, I mean, others are not commenting. If they are fine, if they have any objection, they can let me know. One of you is on hold.
Sanjeev sir. Sanjeev sir.
Yeah. No idea why he's on hold. By the way, if anyone has any objection to this suggestion, he can just write in the chat or let me know by unmuting. Otherwise, I'm going ahead with this. So now, so what contents had week 4? In week 4, your PN junction under equilibrium was discussed. Your PN junction under bias was discussed, and the generation recombination currents were discussed. Okay. So now you had to, in this problem, let's go through this problem. Okay, just let me wait. Someone is typing. Okay, fine. I guess everyone is fine with that then. So we'll discuss week 4 today and wind up the session after discussing week 4. Before continuing, I'll take a quick 3 minutes rest. Okay, I'm a little thirsty. I'll drink water. Okay, just give me a couple of minutes.
Sir, sir. Before break, sir.
Yeah.
Just syllabus part. Just display the syllabus part.
Okay, sure. The syllabus is this. Is this fine?
Okay. Okay.
Okay.
Okay.
Yeah, let's start with this. Okay. In the first problem, we had to calculate the built-in potential VBI of this silicon diode. Now, both the donor and the accepted doping concentrations were around 10 to the power 15 per centimeter cube, right? And notice the temperature, it was maintained at 300 Kelvin. Uh, Given the intrinsic carrier concentration, intrinsic carrier concentration is given. So my Ni is 10 to the power 10. Boltzmann constant. Okay, you can note down the value. The Boltzmann constant value is 1.38 into 10 to the power minus 23 joules per Kelvin. So I'll simply use the formula of this built-in potential, which is kT by Q log of this NA by Ni square, right? And what is my kT by Q? At room temperature, which is 300 Kelvin, that is nothing but 0.026. Is it fine?
Yes, sir.
Fine,
Yes.
right? And this, we need to multiply this by this log of NAND. What is NAND? Both are 10 to the power 15, so this would be 10 to the power 30 divided by Ni square. Ni square, Ni is 10 to the power 10, so Ni square is 10 to the power 20. So this is 10 to the power 10. And if you take log of this 10 to the power 10, which is 2.303 times log of 10 to the power 10 base 10, right? Remember how we use the base conversion here? Mm, or I should say, notice how we use the base conversion. Here it was base E, here it's base 10. These things you already know, right? So this would be log of 10 to the power 10 to the base 10 is 10, right? So if you compute this, this would be 0.6 volts. Okay, simple question. Now the question is for the depletion width, and that too for what? Step doping of silicon that is operated at 300 Kelvin with acceptor dopant concentration of 10 to the power 17 per centimeter cube and donor dopant concentration of 10 to the power 14. Now, okay, so my VBI, uh, just a second. I'll compute VBI from this formula. What will my VBI be? In the similar manner as I computed in the question first, my VBI would be 0.656. Okay. And what else? Now, about this depletion width, right? For the depletion width, the formula is this. The depletion width would be the depletion width on the N side plus depletion width on the P side, right? Xn plus XP, which would be roughly Xn. Why? Because acceptor doping concentration is way higher than the donor doping concentration. So the doping on the P side is way higher. So that means the depletion width on the N side would be way higher compared to the P side, right? So it would be Xn. Now, and Xn we know this would be the formula for that, right? 2 epsilon
Sir,
s epsilon naught. Yeah,
sorry for interruption, sir. You
sure,
told
sure,
that
sure.
accepted doping concentration will be 10 to the 17 and it will be higher than donor density.
Yeah,
So, sir, P type at the concentration higher, so the width of
yeah.
the depletion region is less. Width
Doping,
of the
yes.
depletion is less.
I mean, this is fact, right? The more the doping, this I'm using this formula. See, if your doping is high, then this has to be less, right?
Okay. Yes,
If
sir.
this is low, this has to be high. That is what is getting manifested here.
Okay,
That's
okay,
why
okay,
it
sir.
is. Okay. This is known as what? This is known as charge balance. Okay.
Fine.
Okay. Remember the name. Okay. Charge balance. So, okay. Now Xn would be this. You can now simply compute that by uh, plugging the values, right? So it turns out Xn is 2.93 micrometer. Now from charge balance, you can compute XP. What is XP? XP would be ND by NA into Xn, right? Notice this is Xn and this is your XP. Which is roughly equal to 2.93 micrometer. Why? Because this is how much? Your Xn, what is the order? Oh, here they are differing by order 1, right? Your Xn is 10 times bigger than XP, isn't it?
Xn is 10 times bigger, sir.
Right? Xn is 10 times bigger than XP.
-6 or -7. Sir,
Yeah, minus
how
6,
you can
minus 7.
calculate
That's why
it?
I'm, how?
Yes. I can calculate Xn by VBI. You can put the value of VBI.
Yeah.
X,
We can put the value of the VBI. Rest of the values are known, right? Dopings are known. The permittivities, the free space permittivity and the relative
okay.
permittivities, they are known. Q is known. Every other thing is known.
So from Xn, you can put the charge balance equation to calculate XP, and from that you can
Yeah.
calculate
I
W,
mean, one
Xn
could
plus
one
XP.
could use one could use the equation for XP as well, like I have used in Xn. But why would you do that? I mean, once you obtain Xn, you can simply use charge balance to obtain XP, right? It would
It's quite
simplify
laborious.
the calculation. Yeah. That's why. So uh, the sum of the two would be Xn, right? So that's why your depletion width would be 2.93 micrometer. Now, this third part I have already discussed. You can tune to that session in week 4. It turns out that the concentration of the excess minority carriers in low level injection is large enough to modify this minority carriers, but it's too small to modify the majority carriers, because that's how precisely we define this low level injection. And the question number fourth is a PN junction has a contact potential of this 0.5 volt and the depletion width of 2 micrometer at equilibrium. What then the forward voltage at which the width reduces to 0.4 micrometer is what? Mm, okay, uh, this is the equation of depletion width under a bias. Okay, I'm using a bias of VF, right? So what happens to the depletion width when you apply forward bias to the PN junction?
Depreciation, sir, reduce.
It reduces, right? And it reduces according to this equation, right? More the VF, more will this W decrease, right?
Yes, sir. Yes.
Notice you cannot exceed your VF beyond this VBI, because then this equation would break, right? So this is
Rupture.
technically a limit, right? Yeah, rupture.
Yes, sir.
So, so the qualitatively the thing that I want to take from this equation is that your depletion width is proportional to square root of VBI minus VF, right? Rest of the things are
Yes, sir.
constant, right? This is what
Okay.
depends upon bias. Okay. So now,
Sir,
okay. Yeah.
I have a question, sir. That depletion with under sir under equilibrium, you
Uh-huh.
can also write that W equal to Xn plus XP.
Correct. But why would
From
you,
that also I can.
but why would you, yeah. I mean, if you write that and simplify, take common, it would eventually boil down to this.
Okay.
I'll leave
But
that
sir,
as
this
an
is under.
exercise for you. Okay. Do that thing. Xn plus XP. Uh, Add them, both have a square root dependence, right? We saw it, right? And if you do that, it turns out you'll end up with this equation. If you are getting confused with this bias, here it was VBI, right? Replace this VBI by VBI minus VF, right? For both
Okay.
Xn and
Nothing else.
XP.
Nothing else.
Nothing else. Yeah. And yeah, that is precisely what. Also, now we have been given the depletion width at equilibrium, that is 2 micrometer, right?
Yes, sir.
So depletion width under equilibrium, I won't be applying any bias, right? Because if I apply bias, the Fermi levels will shift, will have quasi Fermi levels, and that won't be an equilibrium, right? I mean, we'll be disturbing the equilibrium in the system equilibrium. So my VF will be zero in equilibrium. Do you agree?
Yes, sir.
So if
No
I
bias
do
is
that,
applied.
yeah, no bias is applied, because at equilibrium you don't apply any bias, right? And contact potential is 0.5, right? This VBI built-in potential is 0.5. So my depletion width under equilibrium is 2 micrometer, and it has to be in this form, k square root of 0.5. Why k? Because there would be some constant here, right? This constant is this square root of 2 epsilon by q na plus nd by na nd. I hardly care of this. All I'm saying is it would be some constant, right? K. Now, and also here it would be 0.5 minus 0, and that would be 0.5, right? So my W1, which is which depletion width is this? Depletion width in equilibrium, right? That is 2 micrometer given in the question, right? Now, what is this W2? This is the depletion width when forward voltage is applied, right? And
Yes,
it
sir.
turns out that your depletion width reduces to 0.4. micrometer, right? Obviously it's reducing, right? From 2 micrometer it came down to 0.4. I already told you, once you apply forward bias, the depletion width reduces. Now the question is, how much is this forward voltage, right? Because there would be a sufficiently high forward voltage which will cause this drop, right? The question is asking, what is the forward voltage? So now, since we had computed this relation, right, our depletion width is directly proportional to this. From this I can conclude this: the depletion width is equal to K times square root of 0.5 minus VF, right?
Yes, sir.
And then what? uh yeah,
Take the
that's
ratio.
it. Then we'll take the ratio. K and K would cancel, because in one case you are applying bias, in other case you are not applying bias. Applying any biases won't change the inherent doping, right? Na was the doping on the p side, right? That won't be changing when the bias is applied, right? So that's why this K and K would go. I'll be left with square root of 0.5 by 0.5 minus VF. From this you can compute VF, and it turns out it is 0.48 volts. Notice it is above this, sorry, less than this. Remember we said it has to be less than this.
What's that near about?
Huh?
But very near to 0.5.
Yeah, I agree, near about. I mean, even if it's near about, the equation would still make sense. It won't be breaking up, right?
Yes.
The problem
Yes.
would occur, say, suppose if I got the answer as
0.52.
0.52, that would be a little problem, because VBI minus 0.5 minus 0.52 is not making sense, right? Because this would be
Negative.
imaginary then. That's why.
Okay.
And then we have the problem fifth, which is as follows: in the given circuit, we have to compute the average voltage across the 2 ohm resistor, right? And we have to consider the following: that the diode has a voltage drop of 0.7 volts, parasitics are negligible, frequency of the input signal is 50 hertz. I discussed this in detail that day. Uh, do one thing, go through that session uh, in week 4. If there are any doubts, you can just mail me. Okay, this would take some time. That's why I don't want to do this. The only thing that will take time here is maths. Okay, physics wise, this is simple problem. The only thing that would
The
take
problem
time.
number?
This is problem number 5. You can note it down. Okay, problem number 5. Okay, this is problem number 5. And then we have this problem. In this problem, what do we have? Just a second. Okay, this is the last problem for today now. A semiconductor has an intrinsic carrier concentration of 10 to the power 10 per centimeter cube. Hole mobility is given. Na and D. Okay, carrier mobilities remain unaffected by doping. Actually, even dopings have, sorry, mobility has a doping dependence. Okay, but in the question it is said that you can neglect that dependence. That's why we won't be considering that. Okay, a PN junction diode with a cross section area of 10 to the power minus 6 per centimeter, 10 to the power minus 6 centimeter square. Remember the area, right? Area is 10 to the power minus 6 here. It's constructed with the semiconductor size as the P and N side both have the dopant concentrations of 10 to the power 14. Both Na and Nd are 10 to the power 14. And what? It's known that the minority carrier lifetime of electrons and holes is same and is equal to 10 to the power minus 6. And the thermal voltage is exactly equal to the 25 millivolts, right? If a forward bias voltage of 0.5 is applied, right, the current through the diode is, what is the current through the diode? Now, what is J? So I can write this equation, right? This is my,
Equation.
yeah. So this is J is equal to Js exponential of QVA by KT minus 1. I'll plug in the values. If I plug in the values for this 0.5 volt, I'll get this answer, right? My J would be Js times 4.85 into 10 to the power 8. This is reverse saturation current density, right? The expression for the reverse saturation current density is this, right? If I plug in the values of mobility, minority carrier lifetime, dopings, I'll get this particular value. This is mathematical exercise that you can verify. This would be 130.50, 10 to the power minus 11 amperes per centimeter square, which if I multiply
Area
here,
divided by.
yeah, if I multiply this here, I mean, the value of the J would be this. If I use this JS here, right? And then I is simply multiplying this by area. Area was 10 to the power minus 6. So if you multiply this, you get I of 0.631 microamps. Fine. So that was
Okay.
your last problem for week 4. I hope this was a useful session for you all. So what we did in
Yes,
today's
sir.
session was I revised first 4 weeks of this course, the problems that I had discussed. If there
The
are
last
any,
request, sir.
yeah, please.
Sir, the theoretical one question you just omit that you can discuss. Should I theoretical
Theoretical
one question
questions.
is there in week
Okay,
4.
in week 4, which question is left?
Yes,
This one?
this, sir. This. Yes, sir.
I'll cover. I'll uh, have a short. What should I say? Short session on this low level injection. I'll teach you in detail if it's needed. I mean, the reason why I skipped this because I would have to discuss low level injection in detail for this one. I'll do that
Okay, okay,
next
sir.
time onwards. Okay. I'll
Thank you,
start
sir.
from this and then see in next session. I won't be revising this week 5 to week 8. What instead I'll be doing is I'll cover today's week 11 and week 12. So in next session, which will be scheduled as per the time. So it won't be this Sunday, it would be next Sunday. Okay, the next session would be the next Sunday. And in that session, I'll cover week 11 and week 12. That would be my week 12 session, but that will have today's content since we did not go through week 11 today. So that will cover week 11 and week 12. Then we will have an extra session after that, a 1 hour extra session. In that extra session, which will probably be on Monday, the next day after that week 12 session. So in that, I'll try to revise this week 5 to week 8. Will that be fine?
Yes, sir. Sir,
Okay.
when you take the small extra session, sir, in between Sunday to next Sunday to this
No, 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 no.
Sunday.
I'll take immediately after my week 12 session. After my week 12 session. When is my week 12 session scheduled? It's not scheduled this Sunday. It is scheduled next Sunday. Right? Immediately one
Yes,
day
sir.
after that will be the extra session. Extra session would be the last session for this series.
Okay, okay. Okay, okay.
Okay. So we have 2 sessions now. Please try to join both of them. Okay. Yeah, that was all
Thank you,
from
sir.
my side. Thank you. We can end the meeting. Okay. Thank you. Thank you for tuning in. Bye.
Bye, sir.
Thank you, sir.